Okay, we've talked about double replacement quite a bit, and we said that it is not redox. Now we want to introduce this idea of single replacement. And single replacement chemistry is different because you have one element reacting with a compound to make a different compound and a different free element. And when we're dealing with this, this is redox because you have an element in its natural state becoming an ion in a compound, and that's what's going on here. And typically the examples we look at are cations replacing, but you can also do single replacement with the halogens where the anion is the element that's doing the replacing, and that works too. Single replacement reactions are redox, and I think they're easier for most students to understand because there's nothing to memorize, you just have to read. These single replacement reactions are driven by the activity series, and you can read a series and it lists things from most reactive to least reactive. So when you look at this, things that are more reactive can cut in on things that are less active. And I used the analogy of the dance before when we talked about double replacement, and I said that double replacement was like trading partners at the dance. Well, single replacement also happened at the dance, but it is not trading partners. The analogy is cutting in at the dance. Now, I told you that I hated dance class, but I never told you why I hated dance class. We'd go in there, girls over on one side, boys on the other side. Mrs. Stromer, dance the girls, dance the boys. Go get 'em, boys. They run over, grab a girl. Everybody's dancing. Ring the bell if people are getting too friendly. That was a double replacement analogy. The single replacement analogy is this. What I didn't tell you the first time is why I hated this class. There were always more girls than boys. Always. So, Mr. Stromer would say, go get 'em, boys. They'd run across the room, grab the girls, and there were girls left on the bench. Always. I know this. In 4 years, I never once ever made it off the bench. It was horrible. So the first time we're sitting on the bench thinking, well, what happens next? Well, what happened next is this. Mr. Stromer comes over and he says to us, Ladies, I'm so happy you're here. You're so special. It's great to have you here this evening. We're sitting on the bench like, yeah, right. That's why we're sitting on the bench, because we're so special. That just didn't work. The guy's 40. I mean, if he said that today, he'd end up in jail, right? So what would happen next is, really, Mr. Stromer would pull a girl off the bench and he'd dance us around. And then I got pretty proficient at most of the steps we were doing. I'm a good ballroom dancer today because of this. So then after he was satisfied that you knew the girl part, he would send you out to cut in on the dance. And cutting in on the dance is single replacement. So you have a couple dancing, and then you have a girl, Mr. Stromer's girl, loose on the dance floor. So this is Mr. Stromer's girl. She comes over, taps on the shoulder of the girl that's dancing. That girl lets go of the guy. This one moves in. They start dancing. Now you have a different loose girl on the dance floor moving around. So loose, not that kind of loose. Loose, not attached to a dance partner. Snickering over there, right? So you had girls moving around the dance floor all the time, cutting in on the dance. Well, I got pretty good at this because I never made it off the bench. So I would be sitting on the bench waiting my turn, and I'd start looking around saying, okay, who am I going to cut in? Well, there was this guy named Mark Pattis. He had jet black hair and the most beautiful green eyes, and he sat next to me because we were alphabetically seated, Nero to Pattis, N-E-P-A. And for years, I wanted to dance with the guy. I tutored him in trigonometry, geometry, and calculus, but we never had any relationship outside of math. So I was watching him dance, and this one day I said to myself as I was getting ready, I thought, you know what, today I'm going to do it. I'm going to dance with Mark Pattis. I'm going to cut in. Now, he was dating a cheerleader with blonde hair named Debbie. I didn't like her, and he always was dancing with her. So I can't wait because tonight's the night. So I'm sitting there, And I'm so ready. I can't wait for Mr. Stromer to dance me around so I can go over there. So I run over to where Mark and Debbie are dancing, and I whack her good on the shoulder to get her attention. Probably harder than necessary. And the most amazing thing happened. She turned her head and looked at me. Mark turned and looked at me. He pulled her tighter, and they danced off. And I'm standing there thinking, what the heck? This is not what's supposed to happen. And it wasn't until I took chemistry in high school that I understood what had transpired that day. Single replacement is driven by the activity series. The active things can cut in on other stuff. Less active cannot cut in. So by my way of thinking, Debbie was way more active than me in high school, which is why he wasn't letting go of that. Right? So the active things do the cutting in. This is an analogy. I know it's a pathetic story of my life, but so, okay, come back to chemistry. So elements can replace things that are less active. And in the process, the more active element is getting oxidized because when you have something cutting in, here I have a free element in its natural state, oxidation number is 0. Now it's becoming a metal ion, so it's having a positive oxidation number, so it's an increase, so it's getting oxidized, right? And think about it. What happens to things when they get oxidized? Iron gets oxidized to rust. It doesn't look as nice. Silver tarnishes. That's oxidation. And I just have to add that I did go back to the high school 20-year reunion, and I saw that Debbie girl, and she looked terrible, and it made me really happy. All right? She looked well oxidized. She looked terrible. I'm just saying. All that activity caught up with her. All right. So, now let's look at a chemistry example. You've got the concept of cutting in. Let's look at the chemistry example. I could use you guys like a laugh track on TV. You're great. And it's not even fake laughter on my videos, right? So let's look at this. Rubidium and manganese. Here's rubidium right at the top of the activity, and here's manganese. So rubidium is more active than manganese. Rubidium can cut in on manganese. Manganese could not cut in on rubidium. Manganese, though, can cut in on zinc, but manganese cannot replace potassium or cesium, barium, strontium, calcium, sodium, anything that is more active than it. So we use this activity series, and we have it written on the paper next to us, and we use this to help us with these equations. So now we're going to complete these equations, writing balanced equations with proper formulas and subscripts, looking at the activity series. So we have iron reacting with gold 3 nitrate. Now, iron's a little tricky because it can be a 2 or a 3 ion. Since it's reacting with something that's a 3, we're going to take the easy path and make iron 3. If it were something like calcium, which is only a 2, then you would have to say, well, calcium is a 2, gold is a 3, and you would have to multiply to make it charge balanced. Yes? Yes, there is a reason, and that reason comes into the way that the electrons are configured. When something gets oxidized, it loses an electron. And so metals that are more active, if you look at this list, they're on the far left-hand side, and we're kind of further down. So rubidium only has 1 valence electron, and it's very willing to give it up. And that valence electron's really far away from the control of the nucleus because that's a very large molecule. So it is willing to give that up more easily than some of the things on the other side.